to this meeting. So today we have a special double bill. So we have two speakers. So we have Mia Hughes from Imperial College and Paul Furey from Humboldt-universität, and she will start the talk. On you go.
Okay. Let's see, just put this. Wonder if I can get the thumbnail. Okay, I guess I'll just leave that then. All right. So first of all, thank you very much to Jose and to Praxiteles for inviting us here to come speak with you today. And also thank you to everybody for showing up to our seminar. So my name is Nichol Furey, and my collaborator, Mia Hughes, and I would like to tell you about some recent results that we found. So I should probably start off by telling you a little bit about my collaborator. So Mia Hughes is a string theorist who has also had a long-standing interest in the octonions. Mia completed her PhD at Imperial College London under the supervision of Mike Duff. And Mia's PhD thesis was on the octonions and supergravity. So I would add that her thesis is one of my favorite introductions to not only the octonions, but also a concept known as triality, which we'll see at the end of this talk. So we've decided to split this talk into two. So I'm going to give the first part of the talk, and Mia will give the second part. And then after this, I'll come back and give a quick comment at the end. Okay, so our talk today is entitled Division Algebraic Symmetry Breaking. And as the title suggests, Mia and I have been looking into particle models which are cast into the language of norm division algebras. So in particular today, we'd like to show you how you can use division algebras to break symmetries. Now, furthermore, I should emphasize that these symmetry breaking methods don't seem to appear naturally when you write these particle models down in the standard formalism. So there does seem to be an advantage to viewing these models division algebraically. So this talk is going to be based on two papers, which we're about to release, or we keep on saying that we're about to release them, but we still haven't done it. But at any rate, the first paper is called One Generation of Standard Model Fermions as a Single Copy of RCHO. And the second paper, which is about to come out, is called Division Algebraic Symmetry Breaking. So this material was already presented for the Rutgers Mathematics Department way back in October, and also just recently a couple of times now at Perimeter Institute. So it's already up on PERSA. So division algebraic symmetry breaking is by no means a new concept. So we're first going to just take a moment to describe some of the symmetry breaking patterns that a number of authors have found by using division algebras. So perhaps the most well-known example appears in the early work of Gunaydin and Gursey. So Gunaydin and Gursey, they showed that the subalgebra of G2, which holds an octonionic imaginary unit fixed, can be identified with SU3 color. Then later in 1999, Jeffrey Dixon proposed a model which starts with spin 19 plus SU2, and he made use of two projectors which are based on octonionic imaginary units, and he used those to reduce this to spin 13 plus the standard model's internal symmetries. Now, much more recently, Michel Dubois-Violette and Ivan Todorov have been working on the exceptional Jordan algebra. And in this work, they demonstrate that the standard model symmetries can be obtained as the intersection of SU3 plus SU3 and the SO9 subalgebras of the exceptional Lie algebra F4. So this produces a commuting diagram from F4 to the standard model via either SU3 plus SU3 or via SO9. So depending on which path you choose, you can view their division algebraic symmetry breaking step as either going F4 to SU3 plus SU3 or SO9 to GSM. Now later in 2019, Karol Krasnoff wrote an extensive analysis on complex structures. And among other things, he emphasized the statement that isolating an octonionic imaginary unit reduces SO9 to GSM, so similar to what Dubois-Violette and Todorov did. And in addition, he also showed an analogous quaternionic result that SO5 reduces to U2. Now, perhaps the result most relevant for what we're going to be discussing today comes from Latham-Boyle in 2020. And there, Latham looked at an SO10 model embedded inside of E6. And from there, he showed that isolating an octonionic imaginary unit can send SO10 directly to the left-right symmetric Lie algebra. Now, after Latham's results came out in June, then our results came out in October. And so we're going to be talking about this shortly. And subsequently, Ivan Todorov has been circulating notes amongst colleagues where he identifies the same result, this SO10 breaking to the left-right symmetric model. And most recently, Kirill Krasnov confirmed that same result, SO10 to left-right symmetric, in addition to also confirming the result that Mia and I first found, which we will tell you about, which is this SO10 breaking to the Pati-Salam model. Okay. Now, throughout this seminar, we're going to be talking, of course, about the real numbers, the complex numbers, the quaternions, and the octonions. Now, the thing I find most appealing about these algebras is not so much the fact that they're special. Of course, they're known to be the only finite dimensional norm division algebras over the real numbers. But more so, I find them appealing for pragmatic reasons. That is, in nature, they seem for some reason to be ubiquitous. For example, you'd be hard-pressed to find a theory in physics that doesn't depend on the real numbers in some way. We're so used to using the real numbers that we don't even realize that we're making a choice in number system anymore. Now, likewise, the vast majority of quantum theories are built using the complex numbers. And whether physicists realize it or not, it's quaternionic structure, or more precisely, complex quaternionic structure, that underpins special relativity and electromagnetism. So some early authors of these ideas include Conway from 1937, and of course also Maxwell from the late 1800s. Now, furthermore, the octonions have been known to be useful for teasing out properties of the strong nuclear force now for decades. So as far as we know, it's Gunaydin and Gursey who were the first to point out that the octonions are good for describing SU3 color transformations of quarks back in 1973. So in summary, these norm division algebras provide one rare example of a set of number systems that is simultaneously unique, but yet is still woven into the fabric of everything around us. Now, in order for everyone to understand the rest of this talk, I'm going to have to arm you with a little bit of technical knowledge. So if you can absorb and retain what's in the next couple of slides, then the rest of this talk should be fully accessible. So please pay attention. Okay, so as you already know, you can think of the complex numbers as being a two-dimensional extension of the real numbers. So here, this new dimension runs along the direction of imaginary unit, which we're going to call I. So by imaginary unit, we just mean something that squares to -1. Now, similarly, you can think of the quaternions as an extension of the real numbers with 3 imaginary units, and we're going to call these epsilon1, epsilon2, and epsilon3. So now when you multiply these quaternionic imaginary units together, then they obey these multiplication rules. So this diagram tells you that E1 times E2 gives you E3, or epsilon1, epsilon2 gives you epsilon3, epsilon2 gives you epsilon1. And then when you go against the arrows, you get a negative sign. So epsilon1 times epsilon3 gives you minus epsilon2. And now finally, we can build the octonions by extending the real numbers with 7 imaginary units. So we're going to call these imaginary units E1 up to E7. And now when you multiply these octonionic imaginary units together, they're going to obey these rather religious looking multiplication rules. So this multiplication diagram tells you, for example, that E6 times E1 gives you E5 and so on. So part of the reason why I'm going through this introduction is so that we can set up some notation. So you'll need to remember that every time you see the symbol I, we're referring to the complex imaginary unit. When you see epsilon 1, 2, and 3, those refer to the quaternionic imaginary units. And then when you see E1 to E7, those are going to refer to the octonionic imaginary units. Now, one thing that I find a little unsettling about this division algebraic symmetry breaking, including our version of it, is the question, why should it happen in the first place? That is, as we'll see, we're going to break these symmetries by isolating one imaginary unit. So a very good question is, why should nature isolate one imaginary unit at all? And you can, of course, ask a similar question in standard particle physics. That is like, why should this particular Higgs field be chosen so as to break a particular symmetry down in this particular way? Now, there is an observation that might end up giving us a clue. And it's related to the fact that multiplication of norm division algebras can lead to Clifford algebras. That is, every time that you've got octonions multiplying octonions or quaternions multiplying quaternions, there's readily a Clifford algebra that arises. So for example, if we were to consider left multiplication of the octonions, let's consider left multiplication of octonions, and here's what this is going to look like. So here at the bottom, we've got the 0 vector, so just given by the unit. On the next level up, we're going to have 1 vectors given by left multiplication by octonionic imaginary units. So you might be more familiar with the notation of a left multiplication algebra. So here on the bottom level here, we're going to have 6 orthogonal imaginary units, which are all going to be left multiplied. So EJ1 up to EJ6. On the next level up, we're going to build bivectors. And we keep on going up, building these multivectors until we get all the way up to the top, and we have a 6 vector, EJ1 to EJ6. Well, hold on, you might say, well, what happened to EJ7, right? Don't the octonions have 7 imaginary units? Well, as it turns out, you can show that this 6 vector always gives the same linear map as EJ7 up to a sign. So saying this carefully, when you populate the generating space by multiplication by orthogonal imaginary units, then the resulting Clifford algebra has a natural way to isolate one octonionic imaginary unit. So does everyone know which Clifford algebra this generates? This is CL06. Now, one interesting, before I move on, so so this is left multiplication by the octonions, and next we can, of course, also consider right multiplication of the octonions on themselves, and we're going to find a similar pattern. So again, we've got 0 vector at the bottom, then we've got the generators given by right multiplication of octonionic imaginary units, then we have bivectors, and we keep on going to the top, where we get EJ7, and again, we've generated another version of CL06.
May I ask a question?
Yeah.
So on your EJ1, EJ2 line,
yes.
So if it's Clifford 6, I'm expecting something with 64, and so are there relations? So on that second and third line and so forth. Otherwise, I'll get more than 64 operations. Why not?
No, so this will be 64. So there are 64 multivectors here in total, and they each correspond to an independent linear map. So this gives a full space of endomorphisms on the octonions.
So that line with 2 has got 30 across, has it? It's got every pair?
So the line with 2, it's 6 choose 2, which is 15.
So I'm trying to understand why the choose 2.
They're ordered.
Yes. Oh, right. Yes, they're Clifford algebras. So they're yes. Good point. So EJ1, EJ2 is minus EJ2, EJ1. Yes. Now
Okay.
I see.
There is a
right there.
relation. That's what I wanted.
Yeah,
And similarly
yeah,
for
yeah,
each of the
okay.
lines above. Okay.
Yes, exactly. So this is part of them being a Clifford algebra. So so when the indices are different, then they're going to anti-commute. Yes. Yeah. Good question.
But
Okay.
if we'd been viewing, sorry, but EJ2, this is left multiplication, and how does non-associativity then work? I mean, F EJ1, EJ2, is that the same as F or minus F EJ2, EJ1, where F was your quaternion?
This is a good question, and it's one of the trickier things to see right away. But Clifford algebra, by definition, is an associative algebra, and so what we're looking at here is the left or the right multiplication maps, and maps by definition are associative. So this is truly an associative algebra. Yeah, I think the way to prove it to yourself is to realize that the left multiplication maps are associative, and so you just have to be careful about brackets. Like there's basically what's happening is that there's two different concepts of multiplication going on. So there's the non-associative concept of multiplication using the octonions. But then there's what we're using here, which is the notion of multiplication is composition of maps, and that's associative. Yeah, good question.
Thank you.
Okay. Yeah, no problem. Okay, so now we've, right, so we have a copy of CL06. So first we were looking at left multiplication of the octonions on themselves, so that gave CL06, and equivalently, as you, perhaps unsurprisingly, when you look at right multiplication, you also get CL06. Now there's one interesting property about the octonions is that whenever you right multiply an octonion onto an octonion, you can always re-express it as always using only octonions multiplying from the left. So to give you an example of what I mean here, if let's say we were to right multiply by the octonionic imaginary unit E7, then you can show that you can re-express it in this way, where you can see that this expression has it has just chains of octonions multiplying from the left. So this particular operator is going to be important for us subsequently in the talk. So it's so important for us that we're going to give it its own name. And we're going to call it left multiplication by the operator capital E7. Okay. So being able to re-express right multiplication by left multiplication is of course also trivially true for the real numbers and the complex numbers, because those are commutative algebras. However, this is not true for the quaternions. So now let's consider left and right multiplication of the quaternions. So we can do just as we did before. So when we left multiply by now epsilon1 and epsilon j1 and epsilon j2, those give us our generating space. And then at the very top level, we've got a bivector, which you can show is going to be equal to plus or minus epsilon j3. So again, we find that when we populate the generating space with multiplication by orthogonal imaginary units, then the left multiplication algebra of the quaternions has a natural way of isolating one imaginary unit. Now, of course, when we do right multiplication, we're going to get a similar pattern. So that's what this looks like here. And now in the left multiplication case, we find that we have an incarnation of the Clifford algebra CL02. And the same, of course, is going to go for right multiplication. But note now that this time you cannot generically re-express right multiplication using left multiplication. So in order to describe the full set of endomorphisms on H, we're going to have to keep both of these. So in the case of the quaternions, we now have CL02 tensored with CL02. Okay. So what are the important things to remember for the rest of this talk? So the first thing to remember is that when we left or right multiply a maximal set of orthogonal imaginary units, we readily get this Clifford algebra structure. So for the octonions, we found that we got CL06. For the quaternions, we found that we got CL02 tensored with CL02. And for completion, I should mention that we also get Clifford algebras for the complex numbers and the real numbers. In the case of the complex numbers, we get CL01. And in the case of the real numbers, we get CL00. So that's the first thing to remember. Now, the second thing to remember is that now in the case of the octonions, the quaternions, and the complex numbers, these Clifford algebras had a natural way of isolating one imaginary unit. So in the case of the octonions, we had EJ1, EJ7, here we had epsilon J3, here we had the complex I, and of course there's no imaginary unit for the real numbers. Now the third thing to remember is that for the octonions, the complex numbers, and the real numbers, you can always rewrite right multiplication entirely with left multiplication. However, this is not true for the quaternions. And the final thing to remember is that when you see this capital E7 operator, what we're referring to is the left multiplication version of right multiplication by the octonionic imaginary unit E7. Okay. So now that we've been introduced to these multiplication algebras, we'd like to somehow put them all together and start talking about particle physics. So let's start by first figuring out how many states that we have in one generation. So in one generation, we've got a neutrino, a charged lepton like the electron. We've got red, green, and blue up type quarks, red, green, and blue down type quarks. So together that's 8. Now each of these are going to be represented by a Weyl spinner. So we're going to multiply by 2. And then we're going to decide to take each of these to have a chirality in left and right. So in other words, we're including a right-handed neutrino. So we multiply by 2 again. So altogether, this is 8 times 2 times 2, which is 32 complex dimensions, or in other words, 64 real degrees of freedom off shell in one generation. So now you might wonder, well, could there be a mathematical object out there which can capture the states of one generation into a single package? Well, what were to happen if we were to take the tensor product of RCH and O? Well, we get an algebra which is 1 times 2 times 4 times 8 dimensional, or in other words, 64 real dimensions. So in other words, by tensoring together, we readily have an algebra which is the perfect size for one generation of standard model fermions together with a right-handed neutrino. Okay, so just some quick notational points. So RCHO is also known as the Dixon algebra. And furthermore, you may have noticed that these are tensor products over R. So RCHO is trivially equal to C cross H cross O. And throughout this talk, I'm going to be shortening this even more. I'm just going to call it CHO. So every time that you see CHO, really what I'm referring to is R cross C cross H cross O. Okay. So what happens now when we left and right multiply this RCHO onto itself? Well, again, we're going to get left and right multiplication algebras, just like we did before with the division algebras. So that is, we're going to get chains of RCHO elements multiplying onto RCHO, kind of like a space of operators that are acting on a state. Now, with these left and right multiplication algebras, they can be brought into the form of a Clifford algebra. And in this case, we're going to get the complex Clifford algebra CL10. So when you repeatedly multiply RCHO onto itself, you can get CL10 structure. And this is great news because once we have CL10 structure, it means that we have ready access to all kinds of particle models. So CL10 sets us up to describe the SO10, or rather the spin 10 model. And as a consequence, we then have access to the Pati-Salam model, the left-right symmetric model, and most importantly, the standard model. Okay, so just to recap, here's an algebra which is 64 real dimensions, or in other words, a perfect fit for one generation. Point number 2 is that just by having this algebra left and right multiply itself, we have access to spin 10 and its subgroups, which means that we have access to all kinds of particle models. Well, hold on, you might say, well, CL10 models, those are, they're already really well known. Like, are you really going to get anything new here that isn't already known within the standard CL10 formalism? And the answer is yes, we are. And the reason is, of course, because what we have here is more than just like the basic CL10 structure. Here we've got all kinds of extra octonionic and quaternionic substructure. So let me show you an example of what I mean. So here's the usual way, or the old way, or the usual way of writing down spin 10 generators in CL10 particle models. So what you would normally do is you just would left multiply the 45 bivectors of CL10 onto your 32 complex dimensional spinner. So in this case, the irreducible representation of the Clifford algebra ends up transforming as a Dirac spinner under the spin 10 group. So this is the old way, or the usual way of writing down spin 10's action. Now, when we left multiply these bivectors onto the spinner in this way, we're going to find that we run into two problems. So the first problem that we run into is that there's obviously no substructure here. So it's not really natural to break the group down. Now, the second problem that we end up with is that the spinner ends up transforming as a 16 plus 16 star. So this now seems to introduce an issue when it comes to building irreducible representations of SL2C. That is, it would be better for us if this thing transformed as a 16 plus 16, because then we could combine them into an SL2C doublet. Now, Mia and I, we have this new way of writing down spin 10 generators in terms of RCHO in a way which has a much richer structure. And here's what they look like. So the S's here, those are real coefficients. And furthermore, you'll notice that the octonionic and imaginary units and the quaternionic imaginary units, they're all being treated equally here in these generators. So this is not a unique construction of spin 10 that works, but it's the one that we find is the most beautiful. So now our new RCHO spin 10 generators clearly supply us with more substructure than just the usual spin 10 version. And now furthermore, we find that in this construction, our one generation now transforms as a 16 plus 16, which solves the spin problem. Okay. So now we're going to rewrite these generators in an uglier form, but in a way that's going to be useful for us. So these are the same generators as we just had, but this will be a useful rewriting of them. So these R's here, these are real coefficients. These epsilons here, these are the quaternionic imaginary units, as you remember. The E's, those are octonionic imaginary units. And this PL here, this is a projection operator, which is going to preserve left-handed states. And this PR here preserves right-handed states. Okay. So now what we'd like to do is we'd like to use this quaternionic and octonionic substructure to somehow break down spin 10. So the question is, well, how exactly are you going to do that? And incidentally, there are several options available to us. And in our first version of this work, we were actually using Clifford algebraic grade involutions to break spin 10 down. But Mia and another collaborator, Beth Romano, suggested that perhaps instead we should try complex structures. So that's what we ended up going with. So what is a complex structure? Well, a complex structure is something that generalizes the notion of multiplying by the complex imaginary unit I. So in other words, a complex structure is a linear map J on a real vector space for which J squared is equal to -1. So now we just mentioned that the set of norm division algebras, of course, has the imaginary unit I. We've got epsilon 1, 2, and 3, and we've also got E1 to E7. So these are all going to make excellent candidates for complex structures. So the idea then is that we're going to use these complex structures to break the symmetries down in a cascade. So there are four possibilities that we're going to consider. So first of all, we're going to consider left multiplication by an octonionic imaginary unit. Then we're going to consider right multiplication by an octonionic imaginary unit. Then we're going to consider left multiplication by a quaternion, and then finally left multiplication by a complex number. So you'll notice that these are all of the options that are available to us using purely exclusively left multiplication. Okay, so we're going to consider these four complex structures. Okay, so now we're ready to apply the complex structures to our spin 10. Now, the nice thing about this part of the talk is you can see for yourself how it works. So here are our spin 10 generators. And now we're going to consider a complex structure given by left multiplication by the octonionic imaginary unit E7, which is being multiplied onto psi, where psi represents an element in our one generation of standard model fermions. It's written, it lives in RCHO. Okay, so we want our spin 10 symmetries to commute with this E7. So you can see how this works. So E7 is going to anti-commute with each one of our EIs or EJs. So if we look at this first term here, you'll see that there's an EI and an EJ. So we're going to pick up two negative signs. Those cancel. So the first term is going to survive. And then if we look at the next two terms, you'll see that there's no EJs, no EIs or EJs. So these are also going to commute with E7. So the whole top row is going to survive. However, if you look at the bottom row here, there's one factor of EI in each of these. So these are not going to survive. So the whole bottom row dies. So here's what we're then left with. So this first term here gives us SO6, or in other words, SU4. And the next two terms, they each give us an SU2, or in other words, together they give us an SO4. So altogether, what we have here is SO6 plus SO4. Does everybody know which model this relates to? This is the famous Pati-Salam model. Okay, great. Okay, so let's move this up. And we're going to repeat the process now. So this time we're going to consider right multiplication by an octonionic imaginary unit, E7. So now when we require that our symmetries also respect this complex structure, we're going to find that it breaks the symmetries down again. And this is what we're left with. So these two SU2s, they're going to survive just fine. But the SO6, it gets knocked down to a U3. Now, incidentally, this is also a well-known model. Does anybody recognize this one? This is the left-right symmetric model. Okay, so we'll move this up again. And we're going to repeat the process another time. So this time, we're now going to consider left multiplication by a quaternion, epsilon 3. And I should mention here that you'll notice that there's a little subscript R on psi. And this is denoting the fact that the vector space being acted upon by the complex structure is given by right-handed particles. So this is how the chirality of the standard model is going to be introduced. Okay, so commuting now with this epsilon 3 in this way subsequently breaks our left-right symmetric algebra down to this subalgebra. So you might recognize these symmetries. This is the standard model gauge group together with the B minus L. Okay, so we're going to move this up one last time. Okay, so we've just reached the standard model plus B minus L, and we've made use of the octonions and the quaternions. So what's the last type of imaginary unit we have left over? The complex I. Okay, so you should know that the complex I is a bit of a special case because I lives in the center of RCHO. So this is unlike the case with the octonions and the quaternions. But this is my favorite part. So does anyone want to take a guess at what the last symmetry will be? Here we find that when you take the standard model plus B minus L, written in this new RCHO language, and you require that it's invariant under the regular old complex conjugate, so just taking complex I to minus I, then we get the standard model's unbroken gauge symmetries together with a B minus L. So the reason why I find this exciting is that we know experimentally that the standard model breaks down to SU3 cross U1, but we don't know from a theoretical perspective, why a Higgs should break it down to this SU3 cross U1 and not, say, some other symmetry. And so the hope is that invariance under complex conjugation could at least be part of the answer. Now, as one final comment, I should mention that there's actually a richer story going on behind the scenes here. That is a richer story than just this cascade of complex structures connecting these models. So this is something that we plan to elaborate on in the near future. And in particular, we can see in more detail what's going on with this B minus L symmetry, which for some reason seems to be lingering. And also we can see what's going on with this subscript R, which appears when we step down from the left-right symmetric model to the standard model. Okay, so let's zoom out now and summarize what just happened here. So first off, we found a new version of the spin 10 model, but which is now written in terms of RCHO. And then we found a subalgebra. We found the subalgebra of SO10, which is compatible with a left octonionic complex structure. We found that this breaks spin 10 down to Pati-Salam. Next, we found a smaller subalgebra still, which now commutes with a right octonionic complex structure. And we found that this step connects the Pati-Salam, breaks the Pati-Salam model down to the left-right symmetric model. Next, we found a smaller subalgebra still, which now commutes with the quaternionic complex structure. And this breaks the left-right symmetric model down to the standard model plus B minus L. And then finally, we found that invariance under complex conjugation gives us a slick new way to go from the standard model plus B minus L to the unbroken gauge symmetries plus B minus L. So the hope is that this last step might lend new insight as to why the standard model symmetries break in the way that they do. So in summary, peering in from the outside, RCHO looks like an ideal mathematical structure for particle physics. It's 64 real dimensional, which is exactly the size of one generation of off-the-shelf fermions together with a right-handed neutrino. Its left and right multiplication algebras realize CL10, so we have ready access to spin 10 and its descendants. However, you might rightfully wonder, if RCHO really provides anything extra that can't already be accomplished by CL10. But we show that indeed it does. In fact, we demonstrated how a cascade of complex structures connects SO10 to the Pati-Salam, to the left-right symmetric model, to the standard model plus B minus L, in addition to the standard model's unbroken gauge symmetries together with the B minus L. Now, these complex structures, they derive from the octonions, and then the quaternions, and then the complex numbers. Okay, so this is the end of the first part of our talk, and now Mia will tell you some further aspects of our model. In particular, she'll recount what I believe is the first explicit demonstration of Quaternionic Triality in the Higgs sector.
Sorry, can I ask a question?
Yes, yeah.
Did I understand correctly? You only have right-handed neutrinos?
I'm sorry, that we have both left-handed and right-handed neutrinos.
Okay, so you can also account for them having mass.
Yes, so we can write down Drac. Yeah.
Right. Okay. Thanks.
No problem. Okay. Okay, so I will exit this and stop share. So Mia, are you able to?
Yeah, I'm just opening it now. Oh. Okay, nice. All right, well, thanks so much for having me to speak here and for coming to our seminar. So I'm going to be telling you some more interesting stuff about this model, some further interesting stuff. So in particular about triality and quaternionic triality that shows up in our model. So first of all, I need to tell you what I mean by triality. Then I'm going to quickly just recap how we wrote down this model, or how the representations work. Then we're going to look at in a bit more detail at this Pati-Salam formulation we've got, and then how this fits in with triality and the Higgs. So let's go for it. So first of all, I need to start with a couple of details about division algebras in general. So like any algebra, division algebras can be thought of as having structure constants. So that is, if you take two division algebraic basis elements, EA and EB, and then multiply them, you get some linear combination of the other basis elements. And these T's, T, A, B, C, they are the structure constants of the algebra, and they just keep track of which one you get. Here I'm using E to mean any division algebra basis elements, so it could be the epsilons or the I's or the octonionic E's. Now another thing that is essential to this is that there is a natural inner product on each division algebra. That is, for any of the division algebras RCHO, if you take psi star chi, where psi and chi are elements of the algebra, and star means put a minus sign on all the imaginary basis elements, and then these brackets mean take the real part of. So you take the real part of psi star chi, then you get the ordinary, basically Euclidean dot product of the two psi and chi as vectors. And what that means for us is that if we multiply two elements of any division algebra, and I'm going to use K here to stand for a generic division algebra, two elements of a division algebra K, so we get this bilinear expression that's also an element of K, and then take the inner product with a third, then we end up with this real scalar, which is nice and symmetrical in these three division algebra elements. So you have V, psi, and chi plugged into the structure constants of the algebra itself. Okay, so that means that each normed division algebra K gives rise to a trilinear form. And that trilinear form is called a normed triality. So we can think of it as being defined. So T of V psi and chi is just the real part of chi star V psi. Now, you might notice that I didn't include any brackets here. What happened to non-associativity? Well, it turns out that when you're taking the real part, it doesn't matter whether I put the brackets on the V psi or the chi star V. So as a convention, you just miss them out. Okay. So what's interesting about this trilinear form is that, first of all, because of the division algebra property, which is that if you multiply two non-zero division algebra elements, you don't get zero. This is non-degenerate, this trilinear form. So that means if you plug in, say, if you plug into just two of its inputs, you get a non-zero covector. That's another way of saying that. And it also has this property that is normed, which it doesn't really matter much for us here, so I won't go into what it means, but those are the two special features of this. Now, normed non-degenerate trialities like this or they're just called normed trialities, are extremely rare. There's one for each normed division algebra, and that's it. So you can see here that if you have a normed triality, that is a non-degenerate trilinear form like this, you can construct a division algebra by making it the structure constants. Or if you have a division algebra, you can construct a norm to triality. So in a sense, these non-degenerate trialities, trilinear forms are, the existence of them is equivalent to the existence of the division algebras themselves. Okay, so now I need to tell you about to define triality algebras. So consider independently rotating each of the three inputs to the triality T. That is, doing a separate rotation, an orthogonal transformation on each of psi, v, psi, and chi, where so each of these matrices belongs to the orthogonal group in dim k dimensions. Then triples of rotations that preserve the trilinear form are called automorphisms of the triality. And so it turns out not just any triple will preserve it. So we end up with a subgroup of basically 3 copies of O dim k. And at the Lie algebra level, the automorphism groups Lie algebras are as follows. So they're called the triality algebras. The first one is just the empty set for the reals. Then we get 2 copies of U1 for the complex numbers, 3 copies of SU2 for the quaternions, and just a single SO8 for the octonions. So these are the automorphisms of the trialities. Now, you might notice that each of these triality algebras consists of an SO dim k, so a part that's the Lie algebra of the orthogonal group in the dimension of the division algebra, plus some extra bit. So we've got SO1, SO2, SO4, and then in the case of the complex numbers, we have this extra U1. In the case of the quaternions, we have this extra SU2. Now, the reason why that's useful for us here is to notice that so under this triality symmetry, we have to transform the 3 inputs, v, psi, and chi, as the vector, the left-handed spinor and the right-handed spinor, or the spinor and conjugate spinor, as it's sometimes called, or semi-spinors, I guess you could think of them. So, sorry, what am I saying? V, psi, and chi of this SO dim k. So at least under just the ordinary SO dim k part, you can look at this as like a v, psi, and chi as vector spinor and conjugate spinor of a single orthogonal group. And with that identification, it turns out that the structure constants T, A, B, C are none other than the Pauli matrix intertwiner corresponding to each of these groups. So they're like the generalization. So what the way the Pauli matrices appear in the off diagonals of the gamma matrices in for the Lorentz group, these T's would appear in the off diagonals of the gamma matrices of SO1, SO2, SO4. Okay, so famously, these triality algebras, they have a discrete automorphism, so a discrete symmetry, which is reflected in the symmetry of their Dynkin diagrams. The SO8 one is the famous one. Less famous is the SU2 plus SU2 plus SU2, but clearly it has the same symmetry. And it's actually the quaternionic triality that's going to be useful for us in the standard model so far. So let me write down then how the 3 reps transform. So we have the vector, which is now explains my notation, by the way, the V for the V, psi, and chi. The vector transforms under left and right multiplication by some imaginary quaternions, the spinor under left and right multiplication by 2 other imaginary quaternions, and the chi again. So each of them has 2 out of 3 imaginary quaternions, which are the thetas. So in sort of particle notation. We've got representation notation. We've got a 2, 2, 1, a 2, 1, 2, and a 1, 2, 2. You might be wondering about my why is there a -1 minus sign out of 6? It's, well, if you look back at the triality, it actually had chi star in it. So in a sense, we can think of chi star as the third element of the trio. And in that case, we've got an equal number of plus signs and minus signs, which explains why the triality is going to be invariant under that transformation. It doesn't explain it, but you can check that they all cancel out. Okay, so that's important. This is important because this is what's going to show up in the standard model. All right, so that was the sort of maths recap. Now let's have a look at go back to our model. So as Cole already told you, an element psi of the Dixon algebra on RCHO has 32 complex components, and that's just right for 16 left-handed Weyl spinners transforming as a 16 2-1 of SO10 plus SL2C. And in other words, that's if you know your guts, that means an element of RCHO is perfectly suited to house one generation of standard model fermions. How do you transform them correctly? Well, Cole already told you, but I'll remind you again. So there is this nice way we found to write an SO10 transformation in terms of just bilinears of the sort of, well, not bilinears, sequential multiplication of the basis elements. So then we have, so ij here, sorry, yeah, I and j run from 1 to 7, and m and n run 1, 2, 3. The thetas, I think, were what called s. So we have this decomposition basically of SO10 into an SO7 part, an SO3 part, and then this off diagonal IMO cross IMH part. Now it has to have this factor of I here, otherwise we end up getting SO7, 3. Okay, now under this action, psi transforms as 2 copies of the 16 of SO10. And notice that this comes entirely from the left. So what about the SL2C, the Lorentz symmetry? Well, while the SO10 acts via left multiplication, the SL2C acts via right multiplication by complex imaginary quaternions, so C cross IMH. So by that I mean linear combinations of ij and k, or epsilon1, epsilon2, epsilon3, with complex coefficients. And if you count up the dimension, that's 2 times 3, 6 real dimensions, just right for the Lorentz group. And also it makes sense at an intuitive level because you know that IMH, or you might know that IMH generates SU2, and then timesing that by I gives you the boosts. And this definitely is going to commute with our SO10 because left and right multiplication in the quaternions commute, as we've said before, or in other words, quaternions are associative. So we do exactly have a 16, 2, 1 of SO10 plus SL2C. So that is 16 left-handed Lorentz Weyl spinners. Okay, so just a quick word about Lagrangians. We can actually write down all the terms in the standard model Lagrangian if we, in this language, if we want to just see it as a recasting of the as either the standard model or any of these guts we've mentioned. We can, if we wanted to just see it as a recasting of the ordinary models, we could write down the Lagrangians for any of them. So just to show you quickly how that would work. If we see psi then as an RCHO valued field in 4D Minkowski space, then we can define a Dirac operator d/psi as follows. Now, remember that we've got SL2C coming from the right by imaginary quaternions. So these I epsilon 1, I epsilon 2, these are like the Pauli matrices coming from the right for the D slash. And the reason for the minus sign on the second one is it's because they're coming from the right. It's effectively like we have to transpose all the matrices before they come. So it's to do with sigma 2 being the only anti-symmetric Pauli matrix, in case you're wondering. So then it turns out then that the free kinetic terms just have this super simple form. It's just I psi dagger D slash psi, just pretty much what you would hope, the real part of that. And it turns out that when you expand all this out into into the quaternionic pieces and finally into the last real pieces, this is equivalent to the kinetic terms of 16 free two-component Weyl spinors. So now if we want to introduce the interactions, all we have to do is take gauge fields valued either in the SO10 Lie algebra or any of the subalgebras that we've mentioned, and then just just promote the partial derivative to a covariant derivative. Now there are obviously other terms in the Lagrangian as well, but I'll get to them. So let's talk about the Pati-Salam model then quickly. It's not, the sections aren't proportionate in time to the size of them, so don't worry too much. I should be finished quite soon. So the Pati-Salam model comes from breaking the SO10 into just breaking the 10D space into a 6D and 4D space. And we've said, or we've shown you already how that can be achieved with these complex structures. This has the effect of breaking psi into two pieces. So psi in RCHO just becomes psi plus and psi minus. And we have, I have to talk you through these labels one by one. So psi plus is a 4 of the SU4 color. It's then a doublet under SU2 left, a singlet under SU2 right, and a left-handed Weyl spinor under SL2C. Then we've got psi minus, which is a 4 bar under SU4 color, a singlet under SU2 left, a doublet under SU2 right, and a left-handed Weyl spinor of SL2C as well. So psi plus here is going to represent the left-handed, one generation of left-handed fermions, and psi minus, one generation of right-handed fermions. And of course, the right-handed fermions here are appearing charge conjugated, which is why they seem to be left-handed. Okay, so that's what the psi plus and psi minus are. So what's all this got to do with triality? Well, within the SL2C, there is, of course, the spatial subgroup SU2 spin. And that means that there is a tri-H subgroup inside our Pati-Salam symmetry group. So that's SU2 left, SU2 right, and SU2 spin of Lorentz spacetime. So sort of lopsided internal and spacetime tri-symmetry. And under this tri-H, the psi plus and psi minus, those left and right-handed parts, transform just like what we saw for the Quaternionic Triality back a few slides ago, except we're missing the third rep, the third element of the trio. So psi plus is like 4 lots of one of the reps, psi minus is like 4 lots of the other one. So is there something around that can be the remaining missing piece, the 2-2-1? I guess this slide spoils the surprise, but it's something to do with the Higgs. So how does the Higgs fit in? Well, how are we going to represent the Higgs? This terrible joke. It begins with an H, so it should be an H, but it turns out to be a good guiding principle because it has, the standard model Higgs has 4 real degrees of freedom and is a scalar with respect to the SU2 spin. So it seems to make some sense to make it a 2,2 of the SU2 left and SU2 right, and a singlet under the SU2 spin and a singlet under the color. So then, and this isn't just numerology. This does actually work, because once you decompose the SU2 right, once you break the SU2 right to get SU2 left and the hypercharge, you find that this does actually decompose into the standard model Higgs. So our four real degrees of freedom become a complex doublet. That is the ordinary SM Higgs. And so finally, I just need to say what became of that triality scalar that I showed you in the beginning, the trilinear form. Well, at this point, it doesn't take much to kind of guess where that's going to come in. In the Yukawa terms, you have just such a trilinear expression with the psi plus the H, the quaternionic Higgs, and the psi minus. So K here is a coupling constant, and tilde means octonionic and quaternionic conjugation together, but not complex conjugation. So it turns out that this is gives you the right. This is the right sort of Yukawa term. It's invariant under SU2 left, SU2 right, and Lorentz. Well, actually the full Lorentz, but including then the SU2 spin, and it's invariant under the color as well. Okay, so then if you now, I mean, you don't need to worry too much about what I've written here. The point is, if you now expand this out into purely quaternionic bits, this turns out to just be 8 copies of the pure quaternionic triality scalar that I showed you at the beginning. Now, as I've shown you them, they all have the same coupling constant, the same Yukawa coupling constant K. But of course, that won't be true at the standard model level. Otherwise, we'd get all the fermions would have the same mass. So it's only at this. So it's only at this Pati-Salam level that we have this triality symmetry. So yeah, it seems at least at the Pati-Salam level that quaternionic triality ties in nicely with the standard model. So just a nod towards the further work, it would be very exciting to find octonionic triality in the standard model. So far, we haven't found a sort of concrete version of this for the octonions. But one possibility is that, so far we've written the electroweak Higgs in our division algebraic language, but there presumably, if Pati-Salam is the next stage, there might be another Higgs field that breaks that. And could that Higgs field be written as an octonion or a complex octonion? And another open question for us that we've been thinking about is, what does the division algebraic multiplication rule actually do for the fermions? It turns out that the leptons have this property that their subsector of the algebra multiply. They turn out to be projectors. They square to themselves, whereas the quarks turn out to be nilpotent. They square to 0. What does this mean? We don't really know yet, but perhaps it has something to do with confinement. Okay, that's it. Sorry for overrunning, and thanks for listening.
So thank you both for your very nice and very comprehensive talks. So questions?
I have a vague question. So I was trying to get a sense of where, in your way of looking at things, it's in some sense more than a elegant reformulation of grand unified theories, and in which sense it's maybe less phenomenological and more predictive than earlier work. It's a vague question, but hopefully you understand what I'm getting at.
Yes, that's a good question. I mean, I think the breaking of these symmetries with these complex structures, so so far that's more of just something we've spotted algebraically that works, gets you the right symmetries. But yes, it would be nice to sort of understand what the physics of that is exactly. I think that's still an open question. I don't know if Cole has more to add. to that. But
no, no, not really. I think, yeah, as we mentioned in these papers, it's not even clear for us if this is if the algebra kind of just gives you a characterization of how to characterize what these subgroups of SO10 are, or if there's a a dynamical, like if there's a Higgs, that should be taking us down from one step to another. So yeah, at this point, it's open.
Okay.
yeah, I think the honest answer is so far it's essentially just a reformulation, but we're hoping for it to go a bit further.
No, these are definitely, it's a nice way of reformulating it. Yeah.
I would argue that it is non-trivial, the fact that these well-known symmetry groups or Lie algebras in physics are connected by by the choice of a octonionic quaternionic complex imaginary unit. That it's at the very least, it's very nice that it worked out that way. You wouldn't necessarily have expected it to generically. You wouldn't necessarily, have expected it to have worked out that way, I guess I would say.
No, certainly not.
Perhaps just a small question, if that's all right. You mentioned that when we had the octonions, we could re-express right multiplication in terms of, some left multiplication of some elements. And you said that wasn't true for quaternions. How generic is that property? If you gave me sort of any non-commutative algebra, or what makes it special?
That's a good question. I'm not sure if you were to look at the whole landscape of every possible algebra, like how often is it the case that you can re-express right multiplication as left multiplication?
I have a feeling it's whenever
you wouldn't expect matrix algebras, for example.
Yeah. I have a feeling it's whenever it's non-associative, whenever it's if it's commutative, then obviously it's trivial. But if it's non-commutative and associative, then I think I wouldn't expect. I think non-associativity, I have a feeling non-associativity is the reason why that works for the octonions. I would need to check to back that up, but I have a feeling that it's the non-associativity that leapt in to the rescue there.
Real. So yeah, and I just don't know if you kind of know the proof, but is it sort of a case of just checking in the case of the octonions, or is there an easier way of seeing it, at least up to a certain amount of permutation?
I found it originally just literally by checking all the linear maps, so in the brute force way. But I'm sure there are. There's certainly symmetries that you can make use of. So once you prove it for one imaginary unit, for example, like what the linear map is, then you can use the symmetries of the octonions to kind of give you the set of the other ones. But I'm sure there are efficient ways to prove it.
I did it a different way, but now I can't remember. I'm just literally trying to open my notes to remind myself, how did I?
That's interesting. Thank you.
Yeah. Yeah. Probably just by checking is the answer.
Nichol, sorry, did you want to make a comment? You said in the end.
I did have a few more slides, but which make some comments about 3-generation work. But I also realized during Mia's section that I took more time than I should have in the first. I didn't want to impose myself.
Sorry, yeah, because I asked for questions very. So I didn't ask you. If you want to say a few words, it's fine.
We were already over time. If people want to see the last slides, I can certainly present them. But we're also at 6:12, so, or 5 for you, I guess.
I don't know. I mean, if you can, if you want, yeah. I mean, we have no time restrictions at the moment. If people want to leave.
I can show you my last slides if people are interested. So what Mia and I have been working on is a 1-generation model, but there was some earlier findings related to 3 generations that we're looking at. So I can show you what those are. Okay, so share screen, let's share. Okay, play. Okay. Right, so this is, so these are, yeah, considerations that I've been looking at with collaborators. And so basically this is based on some, it's a continuation of a 3 generations project from a few years back. And the idea, so for this 3 generations work, the idea is that all of the standard model's off-shell states, including its 3 generations, its gauge and Higgs bosons, they might be able to fit inside the Clifford algebra CL8, which is something that you might find appealing for a couple of reasons. So the idea is to get the standard model states, including the gauge bosons, Higgs bosons, 3 generations, including right-handed neutrinos, into the Clifford algebra CL8. So the first reason why you might consider something like this is just a pure counting argument. So if you know, as you know, the dimension of CL8 is 256 real dimensions. And now if you add up all the standard model's off-shell states, you get 244 real degrees of freedom if you include the right-handed neutrinos. So if you were to then add, say, 12 real degrees of freedom to that, then that would bring you up to the 256 of CL8. So that's the first reason why you might consider it, is that this algebra is roughly the right size. Now, the second reason why you might look at this is because earlier on we found this, there's this a fairly simple action that you can apply to CL8, which gives 220 degrees of freedom transforming in agreement with the standard model under SU3. So there's an SU3 color decomposition of CL8 that gets 220 degrees of freedom transforming in agreement with the standard model. So these lambdas here are the SU3 generators that we're used to using. And the P's here, those are idempotents, which are based on the octonionic imaginary unit E7. So under this SU3 action, we find that CL8 breaks down like this. So here are the irreducible representations under SU3 color. And this C36 here at the very end is a subspace which is misbehaving. But just to give you an idea as to how one possible way to identify these irreducible representations, we can go through and take a guess at what these things could be. So the first 4 copies of the adjoint here, those could correspond to off-shell degrees of freedom of gluons. The next, we could have a photon here and a Z boson. Then the next set could correspond to 6 types of quarks, as you would expect, including their spin and the chirality states. The next set would correspond to 6 types of leptons without right-handed neutrinos. And then finally, one might expect that the missing W bosons, the Higgs and the right-handed neutrinos, could come out of this remaining 36-dimensional space. So this isn't the full 244 degrees of freedom of the standard model transforming perfectly under SU3 color, but it's 220, which is pretty close. Now, finally, if we zoom out, there's actually there's a bigger picture here than just this SU3, the simple SU3 action. We find that it can be generalized to something which I'm going to call a multi-action. So here's an example of what a multi-action might look like, where the dagger can be defined in various ways. Now these P's here, those again are idempotents. And the A's and B's, those are elements of your Clifford algebra CL8. So you can show that this multi-action, what it does is it breaks your CL8 down into 3 different kinds of pieces. So it breaks it down into Lie algebras, Jordan algebras, and spinor spaces. So that is the multi-action it gives you. It's kind of like a universal multiplication rule that works properly on all of these 3 subspaces. Now, one idea is that there could be different multi-actions for different energy scales. So for each energy scale will have its own multi-action or its own multiplication rule. And therefore each energy scale will correspond to a different set of idempotents. So then the idea is that we should be able to relate these different energy scales by coarse-graining these sets of idempotents. Now in this one generation project that Mia and I just completed, we did in fact find different complex structures corresponding to different energy scales. So then the idea would be that we could connect our current results to the multi-action by building its projectors or its idempotents out of these complex structures. So for a couple of years now, I've been circulating these ideas amongst colleagues, and in case you're curious, these details are actually available online. I put them into the appendix of this paper here. So they are on the archive, but they're in the appendix of this paper, so they're in hiding. Yeah, so basically that's it for 3 generation results. Is that basically we have this decomposition of CL8 into something that is close but not exactly the same as what we find for the standard model. Yeah, and that's everything I wanted to say about 3 generations. So thanks again for attending our talk.
Thank you once more.
Thanks.
Thank you. So are there any questions for the new things or for the previous ones? I also have a very naive question. I mean, the things you presented, CL10 and things, smell like higher dimensional origin in the language you use. I mean, does the model you prescribe, I mean, this formulation say anything about that? I mean, for example, the triality of spinate and...
Yes, that's a good question. I guess probably the very short answer is probably no. It doesn't necessarily give us any new insight into whether these symmetries correspond to extra dimensions. However, it's not quite as bad as that, because there are some really nice connections between division algebras and extra dimensions, which I've worked on in a different context in string theory. So, for example, very familiar to everyone is that SL, or physicists, is that SL2C is isomorphic to the Lorentz group, or what's less well known is that SL2O with octonions gives you the Lorentz group in 10 dimensions.
Mm.
So of course you have to be careful about what you mean by 2x2 matrix groups written in terms of non-associative, non-commutative algebra, but there is a way, a natural and sensible way to define SL2O, and it turns out it gives you the Lorentz group in 10 dimensions. So that gives a nice connection just straight off the bat between sort of string theory stuff and octonions, and so in that sense, there's an octonionicness in string theory and those extra dimensions, and there's an octonionicness in what we're doing. So there is a connection but I wouldn't say that it was obvious exactly what the connection is.
There's another thing that you might add as well too. So we get the multiplication algebra of RCHO on itself gives you complex CL10. But then when you split the multiplication algebras into its quaternionic piece and its octonionic piece, basically you get like a CL4 piece and a CL6 piece. So the idea is that you might, without having a concrete way of actually writing this down kind of on an intuitive level, you might hope that the quaternionic piece gives you the space-time degrees of freedom that you see, and that the extra CL6 piece, which is octonionic, would be the extra dimensions, and that, you know, somehow, maybe by merit of the fact of the non-associative, that the octonions are non-associative, that might somehow prohibit these extra dimensions from, you know, being detectable or something. But again, that's more intuition speaking than, or perhaps I should say wishful thinking at this point than anything concrete.
Yeah.
Thank you. So if there are no more questions, perhaps we should thank Nichol and me again.
Thank you.
Thanks for having us.